Good morning. Welcome to Computer Science 221. The last time we met, we found ourselves kind of in the middle, sort of towards the end of Chapter 4. We were talking about the von Neumann machine. Today I'm going to continue about that. We're actually making our ways into Chapter 5, where we're going to start talking about the specifics of the LC3. We've done that a little bit before in the last video, and we're going to continue it on this one. And hopefully in this video we may even get to write a short LC3 program. So first of all, you may recall from the last time, part of the von Neumann machine is this idea that you have this array here that's called memory. And we think of it as a bunch of slots this way. And on the LC3, remember when we talk about memory, you have to talk about the address space and the addressability. Well, the addressability here is 16 bits. And the address space, it goes from 0, 1, 2, all the way up to 2 to the 16th minus 1, which is approximately 65,000. But something we need to get used to here, frequently when we're referring to the memory in the LC3, we write the memory address in hex. So remember, 65,000 to the 16th minus 1, that means it's going to take 16 bits to specify an address on the LC3. 16 bits can be written in 4 hexadecimal digits, so that's how we would write the addresses in hex. All the way up to the very last slot over here is like that. Okay, FFFF. Now, there are several diagrams in your book. They were in Chapter 4. We discussed these things in class. We talked about that inside of a computer there is a main bus. And on the LC3, it's 16 lines. And this is where information and your program and everything else travels around in here. And again, in your book, they have a picture that looks like this. And then we have over here, and we talked about the MAR and the MDR. And remember, what this means is that as we're reading and writing data to memory, we have to specify where in memory we want to put it. Well, if I've got 16-bit address space in here, that means that the MAR is a 16-bit register. Okay, very important point. And then remember that, and the reason why it's 16 bits is because 16 bits we can address anywhere in here using a 16 by 2 to the 16th decoder. So really the way to think about this is that these are actually the select lines for decoder. So, for example, if I wanted to read a certain one of these slots over here, I would put an address on this line over here. Now, if you look in your book, you will see that over here, there is what's called a control line. And control lines can be recognized by the fact that they have these open arrows at the end. And the control line over here, your book calls this the LD.MAR. And what that means is if this bus over here, and remember what this 16 means is it really means there are 16 lines running in parallel. So if I have an address that's on this line here, yeah, this address, these 16 lines are making it down this line here, but they're not loaded into the MAR until this line over here is enabled. Well, remember what's going on over here. The MAR is really a 16-bit register. And remember the way the registers looked. These were all D flip-flops. And remember, they all had inputs coming from them. But there was this one other line here that was very important. It was called the write enable. And that the only time that data actually makes it into these flip-flops here from these lines here is when the write enable is 1. Well, that's what this switch is right over here. This load MAR is really just a write enable line. Okay? Now likewise, coming over here, the MDR, that's also a 16-bit register. And the memory data register basically has two functions. It's either taking data that is in here and it's writing it into memory, or it's taking something that's in memory and it's writing it into here. Now realize this also connects up to our main data bus here, so that, for example, if I had some actual data that was up here, it would get read down here, and just like over with the MAR, what I need over here is I need a control line, and I'll call that LD.MDR. Okay, so that if there's data that's on the bus, the way that it gets in here is by enabling this line here, or setting it high. And remember, that's nothing more than just a write enable line. Okay. Likewise, if there's data coming from here and it's going in this direction here, again, we would have to enable the line, the write enable line, and that's with the LD.MDR. Now, one more thing, there is a line coming up this way that your book refers to as the R.W line. Okay, now remember what's inside of here. Again, these are all going across. These are all D flip-flops, 16 of them per line. And what the R.W line is, that's the read-write line. So sometimes it's actually specified this way. Okay, and this should have an open head on it as well. So there is this R, or this is R.W. And what we know here is that when R is equal to 0, we're reading memory. And when R.W and when R.W equals 1, we're doing a write. So that when this is set to 1, it's going to take whatever is in here and it's going to write it to the address that is specified in here. When this thing is 0, it's going to take whatever addresses are specified in here and it's going to put it over here. Then the other thing that you should note when you look at the picture in your book is that this is also open like that. Okay, there's a control line here. They call this, I think they call this the MDR gate. Okay, which means this controls when anything in here would make it back onto this line here. So now we see how memory rarely works here in the LC3. So let's move on. Now the LC3, inside of the CPU, there are these things called general purpose registers. And again, these are 16 bits wide. And there are 8 of them. So So if we have 8-bit registers, again, thinking about the control lines here, okay, there is a select control line here, and actually you should realize there would be 3 of them, okay, and this is actually a decoder. And the reason for that is it would take 3 bits to specify any one of these over here. So again, and you should get used to this, register 0, register 1, register 2, register 3, over there is register 4, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Okay, so these are called the general purpose registers. Something else you should know about is inside of the LC3 there are these things that are called flags. This is very important. And there are 3 of them. And flags are just 1 bit each. And there's an N flag, and there's a 0 flag, a Z, and a P. And what happens is any instruction that changes a general purpose register sets a flag. Now let me give you an example, and we'll actually see this in a moment. Suppose that R1 contained the number 1 in it. Now I'm writing in hex over here. And suppose that R2 contained the number 2 in it. And suppose I issued the instruction that R3 is to get R1 plus R2. So of course what that's going to do is that's going to change the contents of register 3 to that, and that's positive. So what would happen over here is if I were to look at the flags, okay, and remember there's negative, there's 0, and there's positive. The negative would have a 0 in it, the 0 would have a 0 in it, and the positive would have a 1 in it. If that's not completely clear now, it's going to become clear pretty soon, because we're actually going to watch some instructions execute. Okay, so let's start talking about some machine instructions and actually programming this thing. a couple of things to know about the LC3. The LC3 only has 16 instructions. It's not a lot. Actually, and one of them is unused. So first of all, you could think about the following. If I were to number these instructions, so there might be instruction 0, instruction 1, instruction 2, all the way up to instruction 15. And let's see, if I were to number them, so in binaries, that would be 0, 1, 1, 0, all the way up to 1, 1, 1, 1. The point is as if I give them a unique binary number, I just need 4 bits. And in fact, every instruction is 16 bits. Makes for a nice simple architecture. All the instructions are the same size, so that when we look at instructions, okay, like that, if we were to number these bits from 0, 1, all the way up to 15, okay, it turns out that from bits 12 to 15, that's 4 bits. This is where the number of the instruction is, and that has a very special name. It's called the opcode. So the opcode for any instruction would be in these leftmost 4 bits, and then other information that the instruction needs would be over here. Now, we're going to consider a very simple instruction here right now. It's called the add instruction. And it turns out there are actually 2 forms for the add instruction. So first of all, the opcode for add quite simple enough is 0001. Now the way that the add instruction is going to work is we can say things like this. We can say that register 2 gets register 3 plus register 1. In other words, the add instruction takes 2 registers as input, okay, and it puts the result into another register. Now there's nothing that prevents me from doing this. I could say that R1 is equal to R1 plus R1. And in fact, we might want to do that sometimes. It turns out that there is no multiply instruction on the LC3. So with this has the real effect of saying that R1 gets 2 times R1. Okay? So when we do this, this is what's referred to as the destination register. This one over here is called the source register, but we'll call it source 1. And this one over here is called source 2. So remember we said that it takes 3 bits to specify a source register. So if I wanted to do R2 gets R3 plus R1, well, okay, the destination register is R2. Well, that's a 0, 1, 0. I'm going to draw a line here just so that we can see these things broken up. And then the source 1 register is R3, 0, 1, 1. So I'm going to come over here and say this is the opcode. This is the destination register. This is the source 1. Okay, now here's what's kind of weird. There are a bunch of zeros in here. Okay, and what is going to happen is there is going to be, well, think about it. I've got 4 here and 3, that's another 6, so that's 10. I'm going to use 3 over here. It's going to turn out over here is source register 2. So in that case, I'm going to put 001. Okay, so I've got 3, 6, 9, 13. There are 3 more. There's going to be a 0 here and then a 0, 0 here. And yes, those have to be there. They operationally don't mean a whole lot. I'm going to draw a line over here because it turns out this 0 has a special purpose. But in other words, what this is doing here right now is this is saying take register 1, or no, I'm sorry, it's saying take register 3 and add to it register 1, and it's saying put the result into register 2. Okay, seems a little strange, but why don't we try that out? And by the way, let's do a couple of other things here now. I'm going to rewrite this over here. There are a lot of 0s and 1s in here. And I'm going to regroup them into groups of 4 because I want to write this as hex. So there's a 0, 0, 0, 1. There is 0, 1, 0, 0. 0, 1, 0, 0. There's 1, 1, 0, 0. Okay. 1, 1, 0, 0. And then there's a 0, 0, 0, 1. So that is really 1, 4. And let's see, this is 1, 2, 4 plus 8 is 12, which is a C. And this is a 1. 1, 4, C, 1. So let's hold on to that for a second. Let's get this thing out of the way. And now let's go to an online web page, and I'll post the URL for this on the page. So let me see. I just want to put a 1. I want to rewrite it over here because it's going to be 1, 4, C, 1. And we said that that means that R2 gets R1 plus R3. Actually, it's R3 plus R1. I guess we should be precise here. Okay, so let's get our web page up here. Let's take a look at what's going on here. There's a lot to see. So first of all, here's memory over here, and you'll notice here it's written as 4 hexadecimal digits. And notice I can jump around in memory if I need to. If I just come up here, this started at 3,000. But if I go, I don't want to be at 3,000. I want to be at 4,000. It's taking me to 4,000. If I want to go to some strange hex address, D000, here I am at D000. Well, all right, for fun, why don't we just say 4,000, okay? And over here are registers. So we notice there's register R0, R1, R2, all the way up through R7. I've got my 8 registers right over there, okay? A couple of other things here. I've got my program counter. You may recall the program counter is telling me where the next executable instruction is. Then there's the instruction register right here. That's going to load the instruction that's specified by the PC into here before executing it. And let me see, what else do we have here? I'm not seeing the flags. They will show up, I hope, at some point. Watch what's going to happen. Now, we said here 14C1 is the command to add R3 and R1 and stick it into R2. So I'm going to come over here to memory location 4000. And this doesn't seem to be operating the way that I want it to. What is wrong here? Oh, right here. I'm going to change the contents. And I'm going to make it X, because that is X, 14C1. Watch what happens when I enter it there. By the way, look, it just added this instruction here. Add R2, R3, R1. Now, if I'm adding R3 and R1, I better get over to R3 and R1 and put a number in there. So I'm going to come over to R3 and I click on it. I put the number 3 into R3. In R1, just for fun. Okay, so you can see right now R3 has a 3 in it, R1 has a 1 in it, the other registers are still all 0, and the PC says 3000, but I want it to execute at 4000, so I'm going to come over here and I say OK. So what is going to happen now when I hit step, okay, because I just wanted to execute one instruction, it is going to take this instruction here, it's going to load it into the instruction register, it is going to increment the PC, remember we talked about this in the last video, and then it will execute the instruction. Hopefully when it executes the instruction, it's going to add 3 to 1, and it's going to put the result in 2. So let's just come over here and hit step, okay, and now let's take a look at what has happened. Okay, so here is register 3, here's register 1, and look at what's happened in register 2. In register 2, we now have 4. Okay, we've added 3 plus 1 and we've got 4. Notice that the program counter now went up to 4001. And notice, by the way, I come over here, condition codes, that's what the flags are. Notice it set a P, indicating that the result was positive. Okay? Let's try something else now, just so that we can see this change. Suppose what I want to do, and again, this is just for instruction purposes, so we used registers R1, R2, and R3. Let's use R4, R5, and R6. So in R4, let's put zeros in there. And in R5, let's put zeros in there. And then why don't we let R6 get R4 plus R5. Now, nothing interesting there. It's just going to put a bunch of zeros into R6, but I want you to watch it change the flags. So first of all, let's create the instruction for this. So first of all, add is 0, 0, 0, 1. The destination register is R6. Well, let's see. 6 is 4 plus 2. That's 1, 1, 0. The source register is 4. That's 1, 0, 0. Then I have to put a 0 here, 0, 0 there, and then R5 is 1, 0, 1. Again, this is the opcode. This is the destination. This is R1. This is R2. And now I want to go ahead and write this in hex. Well, that's a 1. Over here I get 1, 0, 1, 1, 0, 1. Well, let's see. That's 4. That's 8 plus 4 is 12 plus 1 is 13. That's a D. Then I have 1, 2, 3, 4. That's a 0. And then over here I get 0, 1, 0, 1. That's a 1 plus a 2 plus a 4. That's a 5. So this instruction here is R6 gets R4 plus R5. Okay, let's put that. Let's come over here just so that we have notes here. So we have 1 D 0, 5, and that is R6 gets R4 plus R5. All right, let's go back to our simulator for a second. We're going to write a 2-line program. So I'm going to come over here, and I am going to make that X1D05. And notice what that is here. I'm going to come over here. Oh, how convenient. Reset all registers. I'm going to reset all registers. I don't quite know what's going on here, but for some reason, there we go. There's our program. Okay, I'm going to come over here in R2. Or no, I'm going to put in R3. I'm going to put a 3. In R1, I'm going to put a 1. Okay. In R4 and R5, I want zeros. R4 has a 0, R5 has a 0, R6 has a 0. I'm going to come over here and I've got to change the first executable line in my program is at line 4000, so I've got to change this to 4000. And I say OK. And now what I'm going to do is I'm going to execute the program. Remember, the program's going to start executing at this line right here. So if I come over here and I say step, I want you to notice that we added 3 plus 1 together. We got a 4. And notice that the condition code here is positive. Now watch what's going to happen. I'm going to add R4 and R5 and put it into R6. We're not going to see anything change here, but we're going to rewrite this 0. And you're going to see that this flag here is going to change to 0. Likewise, you're going to see that this is going to change to 4002. Notice, by the way, currently, what is in the PC. Okay, what is in the PC is the instruction that's at location 4000. When I hit step, it's going to go to location 4001. It's going to load this instruction into the IR. It's going to make this 4002, and then it's going to execute this instruction and set the flag. We should see this P change to a Z. And that's exactly what it did. Notice we're at 4002. So remember, the condition code here, okay, it can either be negative, 0, or positive. It gets set whenever any one of these 8 registers are written to. Okay, I'm going to take a break here, and then we're going to write yet another program. Okay, so we looked at the add instruction. And I should say there are several forms of the add instruction. It was like there would be a destination, 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 source 1, 0, 0, 0, and then source 2. There's also the and this is a logical and the opcode for and is 0, 1, 0, 1. And otherwise, it looks just like add. DDD SS1 0 0 0 SS2. And what that means is that if I wanted to say something like let R2 get R0 and R1, it's doing a bitwise and. So that if R0 look like the following, and R1 look this way, then what would happen is I would do bitwise and, okay, 1 plus 1 is a 1, 1 plus 0 is a 0, 0 plus 1, or I'm saying plus, I mean and. Over here, 1 and 0, 1 and 0, these are both zeros. Here I'd get 1, 1. Over here I would get 0, 0, 0, 0. Over here I would get 1, 0, 0, 1. And what would happen is this would go into R2. Okay? An interesting thing to note here is that if I went ahead and did this, note that the leading 1 over here or the leading bit over here is a 1, and it got written to general purpose R2. My guess, and we're going to see this right in a second, okay, is that this is going to set the negative flag, okay, so that if I wanted to actually execute this, I would do 0, 1, and let's see, my destination register is R2, so that would be 0, 1, 0, and then I would have 0, 0, 0, okay, and then I have to have register 1, like that, okay, opcode, destination register, source register 1, source register 2, okay, and if I go ahead and write this in hex, that looks like a 5, that's going to be 0, 1, 0, 0, that's a 4, it looks like I've got a 0 here, and a 1. Now I've got to stick these values into registers. That looks like it's going to be F, 0, F, and that's a 5. And this is going to be a 9, 3. That is 12 is a C, and that is a 3. So let's see if this works the way we think it's going to work. So I'm going to come back over here. I don't know, I'll come over here and I'll put the instruction here. Let me move my tablet and get my keyboard. So the instruction is 5401, X5401. And notice that this over here, I'm going to come over here, I'm going to clear all my registers. They're all clear. And let me see, what did I say I need to do? R0 has to be F0, F5. And we said that register 1 should be 93C3. What was that? 93C3. And we're going to be sticking the results into register R2. Now I'm just executing one instruction here, and the instruction I want to execute is 4005. So I better come over here and change the PC to 4005. Okay, and I'm going to execute, and remember what we're looking is, let's figure out what we should see. We're going to come over here, this is going to be a 9, that's going to be a 0, that is going to be a C1. That's what we should see when we're done executing this one line of code. So I'm going to come over here and I say step. And first of all, notice it's 90C1. That's just like I said it was going to be. And the other thing to notice is notice that the condition code N is set. Why is it set? I wrote to this thing over here, and when I wrote to this register over here, the leading bit was a 1. That's a negative number as far as the LC3 is concerned. Kind of cool. Okay. Let's do a little more. There is the not instruction, and not just flips bits. Okay, so basically you come over here and you might say something like this: R2 gets not R1. Or if you wanted to, you could even do something like this. You could say that R1 gets not R1. And again, that's just complementing bits. And the opcode for that is 1001. And then what happens over here is I'm going to write this as destination, destination, destination. There is a source, source, source. Okay, and then there's 6 ones. 1, 2, 3, 4, 5, 6. Okay, so for example, if I wanted R1 to get not R1, I would just come over here and write 1, 0, 0, 1, and I would write 0, 0, 1, 0, 0, 1, 1, 2, 3, 4, 5, 6. Okay, and if R1 contained, oh, let's 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 0, 1, 0, 1, 1, 0. Okay, so first of all, let's figure out what that is. That's a 10, so that's an A, and that would be a 9, and that's a 1, a 2, 4, 6. If I were to have not R1, okay, that's going to be 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 1, 0, 1, 0, 0, 1, and let's see, that's a 1 plus 2, that's a 5, 5, and that is a 6, and that's 8, that's 9. Okay, so let's go ahead and just watch that work, just because we want to believe everything that we see. So first of all, we have to come back over here. This would be a 9. I'm working in hex now. The actual instruction. 0, 0, 1, 0 would be a 2. Then I'd have a 0, 0, 1, 1 would be a 7, and then an F. Okay, I'm just converting the binary into hex, so it's 927F. Doesn't matter where I put it, just as long as I set the PC to it. So I'm going to come over here. Let me grab my keyboard. X 927F. And notice that just says not R1, R1. And let's come over here. And what were we going to put in R1? AA96. I need to change my PC to 4008. Okay, and now what I need to do is I'm just going to step 1. It's going to execute this line here, and watch, R1 is going to change, and it changed to 5569, and that's exactly what we calculated it to do. So excellent. That's not. So incidentally, notice that the 3 instructions that we have learned so far, add, and not, these are the 3 operations, and I say the 3 operations performed by the ALU on the LC3. There are no other operations. There are just 3 operations that the ALU does. All of the other operations have to do with moving and storing data and altering the program counter. These are the only things that actually do something to data. Now we're not done. We're done with not, but we're not done with add and. It turns out that there's another form of these, and it has to do, how you recognize the form has to do with looking at this bit right over here. Okay? And I believe that's bit number 5, 0, 1, 2, 3, 4, 5. When the bit is set to 0, we are in what's called register mode. When the bit is set to 1, we're in immediate mode. And the question is what's the difference? Well, when we're in register mode, we're doing something like this. We're doing something like R2 is equal to R1 plus R0. Or we're doing something like R2 is R1 and R0. But sometimes we want to do something like the following. Sometimes we might want to do R2 gets R1 plus 3. Or here's something that's very common. R2 gets R2 plus 1. Or how about R2 gets R2 minus 1? Now the thing to notice over here, the difference between these and these is notice that these have two source registers in them. These only have one source register. So I'm going to say over here there are two sources. And over here, and the same thing happens in AND. I could say something like, this makes a little less sense. R2 is given to R3 and 3. Now we can do that on the LC3, and it's a little bit unusual, but it is doable. Over here what's happening is there's only one source with one literal. Okay? And here's the literal. In this case, the literal is 3. In this case, the literal is 1. So again, if we go back and we look at the AND instruction and the add, let's look at add. So add is 0, 0, 0, 1. And let's look at this instruction right over here. And here's the add instruction right up here. How convenient. So the destination is DDD, so the destination is 2 here. So it's 0, 1, 0. And there is a source destination here, which is 1. Okay, so that's 0, 0, 1. But now, instead of being in register mode, I want to be in immediate mode. So I'm in immediate mode, I put a 1 here. And now the thing to realize is I've got 5 bits over here that I can specify a literal number. Now this is to be interpreted as a 5-bit signed integer. Okay, so that if I wanted to add 3, I would go 0, 0, 0, 1, 1. And what this is doing over here is this is saying that R2 is getting R1 plus 3. Now this is very common over here. Okay, this is the kind of thing that we very frequently see in a loop counter. So that would be, so this is A, and that's A. Let's call this B. So here's B. So again, I would go 0, 0, 0, 1. Okay, and this is R2, 0, 1, 0. The source is R2, 0, 1, 0. I want to be in immediate mode, 1. And what I want to do here is I want to put the number 1. 1, 2, 3, 4, 5. So if I wanted to say R2 is equal to R2 plus 1, this would be the way to do it. If I want to do C over here, I want to subtract 1. Okay, now the problem is I want to know how to write minus 1. Well, I'm working with 5-bit signed integers. If this is 1, then if I want to calculate minus 1, what I need to do is find the 2's complement of this. Well, first I complement it, and then I add 1 to it, and I get this. Okay? That's immediate mode. Very, very, very useful. Let me ask you something, a thought question for all of those folks out there. I want to know, what does this do? Okay, well, let's see. We have to go back and check our notes, and we have to look up, what is this? This is AND. This is a destination register. This is source 1. This represents the fact that it's immediate. This is the number 0. So what this seems to be doing is this seems to be doing that R2 is getting R2 and 0. What does that do? Well, that puts a 0 in R2. Or stated another way, it clears R2. And this is the standard way for clearing a register. If I want to clear R7, R7 gets R7 and 0. Put a Java comment in here. Clear R7. Now the question is how do these immediate mode operations work? And again, I refer you back to your book for the picture. My picture isn't going to look so good. I'll try it here. If you look in your book, you can see we have the ALU over here. And up here, these are our registers. And the registers certainly form one of the input lines to the ALU. Now they also form the input line to the other side of the ALU. But what happens over here is there's a MUX. Because remember what happens, and then there's a line coming out of here, but there's another input line over here. Because remember what happens, if I'm adding two registers, then yeah, I've got a register going in here, and I want, going through the MUX, I want the register coming through. But there's another possibility over here. The other possibility is that I'm either doing an AND or an ADD, and it's in immediate mode. So over here, here is the instruction register. And over here, the rightmost 5 bits, this goes into, in your book you'll see a lot of these, but here's one of them right now. There's a box that is called SEXT. And that stands for a sign extension register. And basically what it does is what's coming up here is 5, but what's coming out of here is 16. Okay? Then you'll notice over here, if this is a MUX, there's got to be a control line to the MUX, saying which one of these do I use? Well, the answer is very simple. It's this bit right over here. Okay, remember this bit is either a 0 or a 1. Okay, if it is a 0, that means that we just let whatever the register is come over here and go down in there. But if it's a 1, then that means that this, the sign extended 5 bits, is going to be the input. So this would be, if there's, this would be 0, this would be 1. And then of course the output here cycles around and goes back to the register like that. Okay, kind of cool. And I want to finish up, I want to write one more program. do something really complicated here. How about if I were to say to you, I want R2 to get R1 minus R0. Okay, now on the LC3, there is no minus sign here, but we know we can do this the same way as doing this. It would be R1 plus a minus R0. So what I need to do is somehow or other, I need to get the 2's complement of R0. Well, I can do this in a couple of ways. Now, first of all, what I could do is I could say, well, first of all, let's put, I'm using R0, R1, and R2. Why don't I let R3 get not R0? And then why don't I say to R3, let's add 1 to it. So I'm going to say this is minus R0. And then what I want to do is I want to say R2 gets R1 plus R3. That looks like it does it. The other way I could do it is I could do the following. I could say let R0 get not R0. And then I could say R0 gets R0 plus 1. But what this has done is this has destroyed whatever was in R0 originally. Now that may be perfectly permissible, it may not be. I don't know. So what I'm going to do over here is first I'm going to call this, so it doesn't take too many lines to do this, A, B, C. So the first thing I have to do is look up not 1001, okay? And my destination register is R3. My source register is R0. Okay, and then I have to go 1, 2, 3, 4, 5, 6. So that is A. Let's break that up into hex. So that is a 9. And then I get 0, 1, 1, 0. Let's see, that's 2 plus 4 is 6. And then I get 0, 0, 1, 1. That's a 3. And then an F. And now B, R3 has to get R3 plus 1. Add is 0, 0, 0, 1. R3 is going to be 0, 1, 1. 0, 1, 1. I'm working in immediate mode, and it's going to be 1, 2, 3, 4, 5. So that's going to be 1. Then 0, 1, 1, 0 is, let's see, that's 2 plus 4 is 6. 0, 1, 1, 0. Then I get 1, 1, 1, 0. Let's see, that is an E. And then a 1. And then finally in C, I'm going to get R2. So that's an add. And the R2 is a 0, 1, 0. R1 is 0, 0, 1. Now we're in register mode, so there's a 0 and then a 0, 0. R3, 0, 1, 1. So that is a 1. And 0, 1, 0, 0 is a 4. 0, 1, 0, 0, 0, 1, 0, 0 is a 4. And then 0, 0, 1, 1 is a 3. So there's my program. And let's run this one. So I'm going to come over here. I'll put it back at 4,000. 963F. Here I'm going to put 16. Oops, that didn't take. X16E1. Here it's going to be hex 1443. And now I've got to put some numbers in here. Let's have fun. So I have to put numbers in R. It's going to go R1 minus R0. Let's clear all the registers. So let's put 3 in here. Oh, let's have fun. Let's put 13 in here. And let's put 3 in here. So R2 should get R1 minus R0, so R2 should end up getting a hex 10 in it. Where did my program go? Hang on. There's my program right there. Okay, so remember what we're going to be doing is R2 is going to get R1 minus R0. So R1 minus R0, what we expect to see in here would be hex 0010. That's going to be positive, so the condition code should be P. Okay, so let's step through this one line at a time. So first of all, R3 over here we've inverted. We have inverted R0. Now we're going to add 1 to it. Okay, and now we're going to do the add. And notice when I did the add, notice now I've got a 10 here, and notice that the result was positive. Okay, so it went 13 minus 10 is 3. Let's do something a little interesting here. Let's make this number bigger than 13. Why don't we make it 17? Why don't we come over here and set this back to 4,000? Okay, and why don't we run it again? Okay, so what's going to happen now is the result R3, if I'm going to go 13 minus 17, it seems to me I should get minus 4 in there. So I step, step, step. Okay, and what is going on here? Something got changed here. Oh, I put things in the wrong registers. That's what's going on here. I need to put something in R1 and R0. So here's a 13, hex 0017. Okay, let me set this back to 4,000. Okay, I'm going to go step, step, okay, step. Okay, so now I went 13 minus 17. It gave me this number here, and notice I've got a negative. Okay, and I'll leave it as a homework assignment for you to verify that that is in fact the number minus 4. Okay, I think I'm done. I hope you all enjoyed this. You should start playing with this coding. It's a lot of fun. Okay.